Right, hi everyone. So this is the first video that I've made in quite a long time, but now I've got a bit of free time, so I thought I'd get back to it. Now a lot of the previous videos that I've made have been talking about machine learning approaches, with occasionally a bit of programming. Now I've decided to go in a slightly different direction with the next set of videos, and really we're going to talk more about linear algebra. That's because when you start to really pick apart these machine learning methods and try to understand the maths that lies within them, which is ultimately what you need to do if you want to know how these things really work, a lot of the concepts that come out are really from linear algebra. And so it's important to have a kind of basic understanding of this branch of mathematics if you're ever going to really understand machine learning. So today we're going to talk about the power method, which is a way of computing the dominant eigenvector of a matrix. So we'll just define what that means. So we're going to have a square matrix A, and for now we're going to say that it is symmetric. You don't actually have to assume this, but it's helpful for the following proof. And in fact, in the next video, we might explore what happens if A is not symmetric. And we're going to say that A has some eigenvectors, which we'll write as V's. So we've got a V1, a V2, and so on, up to the width or height of A. And for each of those, there's a corresponding eigenvalue. So lambda 1, lambda 2, and so on. What we're going to do is we're going to assume that these eigenvalues have been ordered so that the magnitude of lambda 1 is the largest. So in other words, the absolute value of lambda 1 is larger than the absolute value of lambda 2, the absolute value of lambda 3, and so on. What the power method lets us do is it lets us find what's called, as I said, the dominant eigenvector. That is the eigenvector that's associated with the largest absolute eigenvalue. So in other words, because lambda 1 is going to be the largest absolute in our problem here, then the power method is used to find V1. So this might not be the most efficient approach to do this, and in fact, as you can imagine, there's lots of different ways of calculating eigenvectors and eigenvalues of matrices, but it establishes some important concepts, and the power method often, when you see more advanced methods, when you work backwards slightly, then you realize that actually it's a variant of the power method. So understanding the power method first is really important. So how does it actually work? Well, what we do is we start off by generating a vector x, possibly just randomly. The choice of this vector is something we might cover in the next video, but let's just say for now that it's picked randomly. And x has the same length as the size of our matrix A. So if A is n by n, then x has length n. Then we're going to pre-multiply it by A, and then pre-multiply it by A again, which we write as A to the power 2, multiplied by the vector x. We keep doing this k times until we end up with A to the power of k multiplied by x. What we're going to show in the following proof with some code at the end is that this vector here converges to V1, i.e. the dominant eigenvector. So it's a very simple approach to implement. And so what we're going to do next is just go through a proof to establish that it works. One key thing to note before we go into the proof is that by assuming that A is symmetric, we've got orthogonal eigenvectors. So that means that if you have one of the eigenvectors, let's say transposed multiplied by a different eigenvector, and this is equal to 0 for I not equal to j, whereas if you have the same eigenvector, the dot product between the same eigenvector, so I and I in this case, then you'll get something that's non-zero. In fact, in the following, we'll assume that all of our eigenvectors have been normalized, so that vi transposed multiplied by vi is equal to 1. So we'll start by talking about taking an eigen decomposition of A. So this might be something that you know about already, but we'll go through it relatively briefly. So here's our basic definition, where we've got our matrix A, eigenvector Vj and eigenvalue lambda j. If we pre-multiply by a different eigenvector, so let's say Vi on the left-hand side, transposed, and that's equal to, so the eigenvalue is a scalar, so it will come outside this matrix, or rather vector multiplication. We have a Vi transposed Vj, and we already know that this is equal to 0 because they're different eigenvectors and they're orthogonal, and so we're saying that Vi transposed A Vj is always equal to 0. If we had pre-multiplied by the same eigenvector, then we end up with, again, this is a scalar, lambda j multiplied by the jth eigenvector transpose multiplied by itself, and we already know, because they're normalized, that this is going to be equal to 1. Okay, so from that, if we create this matrix V, which is, so this is sometimes called a block matrix, but basically we write it like this. It's a matrix whose columns are equal to the different eigenvectors, so each of these is a vector going downwards. Then what you can do is, after a bit of maths, you can show that that matrix transposed multiplied by A multiplied by that matrix is equal to, you end up with something that looks like this, where you have your first eigenvector transposed times A times your first eigenvector. Here we have the first eigenvector transposed A, second eigenvector, and so on. Okay, which looks like this. Now from these two properties up here, hopefully we can see that all of these off-diagonal terms will be equal to 0, and all of these diagonal terms will be equal to the corresponding eigenvalue. Okay, so that comes out as being equal to eigenvalue 1, eigenvalue 2, and so on, with zeros everywhere else. So we'd usually write that by saying that V transposed A V is equal to D, where D is, I'm not sure how I did that, diagonal lambda 1, lambda 2, and so on. Okay, now because this matrix V is made up of orthogonal vectors, so our eigenvectors, orthogonal, which we've used here, for example, that property, that it means that if you multiplied V by V transposed, then you get the identity matrix. Likewise, if you multiplied V transposed by V, you would get the identity matrix. So if we take this and we pre-multiplied by V, you have a V transposed, A V is equal to v multiplied by d. This thing's equal to identity, so we can just ignore it. You can then take this expression, post multiply by v transposed, then you get a v transposed is equal to v d, again post multiply by v transposed. This is equal to identity, and so you end up with being able to write your matrix A as equal to this matrix of eigenvectors times the diagonal matrix of eigenvalues multiplied by this matrix of eigenvectors transposed. And so that thing is our eigen decomposition. So now what we're going to do is we're going to use that to explain why the power method works, i.e. converges to the dominant eigenvector. Okay, so we said that with the power method, we start off with some vector and we pre-multiply it lots of times by the matrix A. So let's just investigate that a bit further. So for example, if you have A multiplied by A, then now using our eigen decomposition, we know that that is also equal to V times diagonal matrix D times V transposed. And again, so that's A times A. And then we can note that you could write this as being V times D. And all I'm doing is moving the brackets here. It doesn't matter, but it's just to make it clear. So this is exactly the same equation, but now just making it clear that this in the middle, that is equal to the identity matrix, as we know, because V is orthogonal. So we end up with that being equal to V times, so this matrix D times itself, so we write that as a D squared times V transposed. If we keep doing that lots and lots of times, like I say, the power method involves pre-multiplying lots of times, say k times, by the matrix A. So if we consider, we extend this so it's A to the power of k rather than just the power of 2, then hopefully you can see you would end up with this matrix V times diagonal matrix to the power of k times this matrix V transposed. Okay, as a final step, we're just going to post multiply by V again. So what we've got is that A to the power of k is equal to V, multiplied by V is equal to V diagonal matrix to the power of k. And then we have a V transpose on the end, but again that's equal to the identity matrix. Okay, so we've got these two relations here. Now what we're going to do with our power method is we're going to start off with some initial guess at our dominant eigenvector. So I'm going to write that as an x, and I'm actually going to write it as an x with a kind of tilde on the top. And let's just say we've got this somehow, and in fact you might have just generated this randomly. So that's what we'll consider here. So randomly generated. And what we're going to do is going to imagine, and this is kind of the trick of the thing, so we don't have this matrix V yet, we don't know the eigenvectors, but the trick for this proof is we're going to say, well then we're going to, let's just imagine we've got some vector x which is equal to the matrix V times our randomly generated initial x. Okay, so just kind of, we're just going to believe that and follow it through. So now if we write down a to the power k multiplied by x, then we know that that is equal to, so we've got this definition of a to the power k up here. So that's going to be equal to v times d to the power of k. Really don't know why that keeps happening. Multiplied by v transposed x. We then substitute in this definition we've created for x here. So that's equal to v d to the power of k times v transposed, and now this comes in. So v x tilde. This is going to be equal to the identity matrix. Again, v is orthogonal. So all of this is then equal to v d to the power of k, and then this our original randomly generated x. Okay, so what can we do with this? So we've got v times d to the power of k. So just like with any matrices, if we've got two square matrices of the same size multiplied together, so standard matrix multiplication rules means that v times d to the power of k, and I'm going to look at the ijth element of this matrix, is equal to summation of, so I'm going to introduce a new index here, n, and it's just going to be n over the height / width of either of these matrices, and it's the nth element of v times the njth element of d to the power of k. So that's just your standard definition of two matrices multiplied together. And the key thing to note here is that because d is still diagonal, even when it's to the power of k, it's still diagonal. Then when you compute this summation, the only place where it's going to be equal to anything that's not 0 is at the jj. Okay, because that is the rest of that row, if you like, or column rather, is going to be equal to zeros. So this comes out as being the only non-zero term is when n is equal to j. So we end up with v I j multiplied by d to the power of k j j. The diagonal elements of d at this point, remember that d is just the eigenvalues on its diagonal, so d to the power of k has the eigenvalues to the power of k on its diagonal, so this all ends up being equal to v ij times the eigenvalue, jth eigenvalue to the power of k. So if you then go to write this down in full, what you end up with is that this matrix V times matrix D to the power of K can actually be written in kind of block form, if you like, as being eigenvector 1 times eigenvalue 1 to the power of K. So that's one column. The next column will be made up of eigenvector 2 times eigenvalue 2 to the power of K, and so on. That means that, again, returning to this up here, so essentially we're just trying to expand this term. Matrix V times D to the power of K is equal to everything from the previous line. Remember, those V's are vectors. Multiplied by, so this x tilde, I'm actually going to split that up into individual elements, scalars. So let's say that's x tilde 1, x tilde 2. Okay, so these, which are hopefully coming out as bold, these are vectors, the eigenvalues are scalars, and these are now scalars. So this is the vector x tilde, just with its individual elements written out. So then this becomes equal to, so standard vector by vector or matrix by vector multiplication applied here. Sorry, I forgot to say, we are now post multiplying by x tilde. Like I say, we're expanding this term here. So that becomes equal to basically just the summation of however many terms we've got, i.e. the height or width of the original matrix A of the, let's write it here, the jth eigenvalue to the power of k times this vector v multiplied by one of these scalars from our originally randomly generated vector x. And what we're going to do now is we're going to extract from that the largest eigenvalue. So we're going to assume that lambda 1 is the largest eigenvalue. So when we say we're looking for the dominant eigenvector, it means we're looking for v1 essentially. So all I'm going to do is take that outside of the summation. So it means that this will be equal to lambda 1 to the power of k multiplied by the summation over j of lambda j divided by lambda 1 all to the power of k, and then everything else is the same. Okay, so all that's happened here is that lambda 1 to the power of k has just been taken outside of this summation. Okay, and if we go up to here, then we can remember that we started off essentially by expanding a to the power k multiplied by the vector x. So we can write that down here. So a to the power k multiplied by x. And we've already defined lambda 1 as being the dominant or the eigenvalue associated with the dominant eigenvector. So we're saying that lambda 1 is the largest eigenvalue, or more specifically, the absolute value of lambda 1 is larger than all of the other absolute values of the eigenvalues, and so on. So what that means is, when you look at this ratio that comes inside this summation, for j equals 1, then, okay, we have a lambda 1 divided by lambda 1 here, so this term just becomes 1. For all of the others, whether it be positive or negative, the absolute value of lambda j for j equals 2, 3, 4, etc. will be smaller than the absolute value of lambda 1. And then when you put that to the power of k, and k gets larger and larger, then all these terms will converge to 0. They'll become very, very small. So as k gets large, the only term that's really left in this summation occurs when j is equal to 1. So what we can say is that a to the power of k multiplied by x will therefore tend towards, so we're just going to leave in here the stuff that comes up when j is equal to 1. So we have this cancels. We have a lambda 1 to the power of k here. We have a constant, which I'm just going to move to the left of that vector v here. So that's that's when j is equal to 1 as well. And then we've got this vector v1, where if you remember, v1 is the first eigenvector. It is the eigenvector associated with lambda 1, therefore it is the dominant eigenvector. So we say as k tends to infinity. Okay, and what this means is that this vector here is going to tend towards something that is proportional to the dominant eigenvector. We only ever know the eigenvectors up to a constant of proportionality, so usually we standardize them so they have unit length, for example. So in your power iteration algorithm, each time you calculate a new estimate of v1, then you might normalize it afterwards as well. But the proof is essentially complete here. It says that as k goes to infinity, a to the power of k multiplied by x must tend to something proportional to the dominant eigenvector. Okay, so here's some example code in Python. So let me know if you'd like a copy. It's very simple. All I've done here is make some kind of symmetric matrix. I've computed the eigenvalues just using NumPy's linear algebra library, just for the sake of comparison. Here, all I've done is extract the dominant eigenvector, which I've written as v1. And then just so we can plot a comparison, I've made sure that the first element of the eigenvector is positive. Okay, so again, that's just for the sake of plots, because you can have, as we know the eigenvector only up to a constant of proportionality, then you could multiply it by -1 and it'd still be kind of correct. So I've just made sure that the sign's the same for the eigenvector that's calculated using NumPy's library and the power method. Again, that's just so we can plot them on top of each other. I've got a randomly initialized vector x. It's going to go through this loop. So we're going to plot the random initialization against the true dominant eigenvector. Here's a power iteration method. So we pre-multiply by a. We normalize it to be unit length, as I said. Again, this is just to make sure that the first element of our estimated dominant eigenvector is positive. And then all we're doing here, bad notation there. All we're doing here is plotting the two on top of each other, i.e. we're plotting how our estimate converges. And as you can see here, well, initially the estimated eigenvector, i.e. shown in red, has been randomly generated, and then you can see over subsequent iterations that we converge. Okay, so that's that for this video. I think in the next video we will perhaps look at this in a little bit more detail. Specifically, we will think about what happens if your matrix isn't symmetric. So that was one of the conditions that we had, that actually you can relax slightly. And we'll also talk about how you might need to initialize your random vector here right at the start of the power iteration algorithm. But for now, I think that will do.